still have the session? Is the session still going? Is the quiz still going? I think the quiz has just wrapped up, and we are just about to go live. We're just about to get started. All right. As we're about to get started, let me see. Can I put some slides up? If you haven't yet filled in the survey, hello, Jua, if I'm pronouncing it right in the chat, hello to you as well. If you haven't yet filled in the survey, you should go for it. We're trying to understand the patterns in how open your data actually is. We'll try to share those with you afterwards so that everybody gets a good sense of what's actually happening in the industry. Fill in the survey, it'll take you just 30 seconds, and it will make us very happy. I'm your host, again, for today. I am very excited to have Amaresh join us. Amaresh, can you hear me okay?
Yep.
You're on stage. All right. Amaresh, where are you dialing in from?
I'm from the Bay Area.
From the Bay Area. And today, you're at Peloton.
Yep.
Right?
Yes.
You're going to talk to us about how open table formats can actually be used to reduce latency. Is that fair?
Yeah. Right. Yes. Yeah. That's fair.
I think a lot of people will have questions for that. I'm going to get off the stage as soon as I can so that we can leave some time for questions in case we do have any. I'm going to be back in about 10 minutes. We'll see you soon.
Yep, sure thing. Hey all, I'm Amaresh Bingumalla, currently working as a senior data platform engineer at Peloton. Thanks for joining my talk. Today I'm going to be talking about how our team used open table formats, mainly to boost querying and reduce latency for faster data access. Before I dive into how we achieve that, I want to give a little bit overview on what the existing architecture was and what changes we made to actually get that impact. So if you see here on the left, these are the Peloton devices. Peloton is a digital fitness platform. So we have Peloton bikes, Peloton treadmills, Peloton rows, and the Peloton apps on the web, iOS, and Android. So these Peloton devices, of course, talk to microservices, and then these microservices do CRUD operations on RDS databases. We also use DynamoDB tables as our NoSQL needs. I'll talk about that in a bit. But yeah, these microservices do CRUD operations on RDS, and most of our databases do have read replicas depending on the load and the need. So these read replicas are used for our recommendation systems or the analytical use cases. So we use Redshift primarily for our analytical workloads. So on these read replicas, we do have daily snapshots and hourly incremental snapshots. We use the hourly incrementals to send it to Redshift. So Redshift, like data engineers or analytical data analysts can do analytical workloads and then push them to Looker for operational dashboards. We also have the daily snapshots from these databases. These go in and sit in S3, and these are used by recommendation systems for training ML models and push the recommendations to the devices. So this is the existing architecture. As you can see, there might be some challenges or some flaws in this. So the main or the first obvious one is the dependency on the daily snapshots. So both the reports, dashboards, and the recommendation systems are constrained by the daily snapshot. So if for any reason the daily snapshot is not done, the recommendation or the training pipelines and the dashboards are stale or cannot move forward. It could be any reason. I mean, there is a load on the database or the maintenance is happening on the database, so the snapshots are delayed. So this tight coupling between the online and analytical systems is not ideal. I mean, due to maintenance on the database, I shouldn't have a delay on my dashboards or training pipelines. They should be decoupled, and there should be a better way than this. Um, there are higher costs and load on the database read replicas because doing a data dump on like an RDS instance or like a Postgres or anything puts load on your primary database, which is actually backing your production service. So any ad hoc queries or even like a data dump for snapshots does increase the load on the database, and that's not an ideal situation which can actually affect your customers. And the last one, so during a data migration, like you're moving to a new database or you're trying to split off into a new microservice, there is no easy way to do this without client handling the dual rights. So there should be a better way to assess the services or the product engineers to do it quicker, and they don't have to worry about how are they going to migrate from one database to other database or like split off into a new service. So the solution or part of the solution, major part of the solution are open table formats. So a quick refresher, open table formats are open source standard for storing data in blob storages like S3 or Google Cloud Storage on top of existing file formats like Parquet or Avro or ORC. So on the right, if you see Apache Hudi, Iceberg, and Delta Lake are the top three open table formats used across the industries. All three share a similar fundamentals at the base level. So they do store data in the same file formats that we know. Like most of them use Parquet, Avro. Along with the data, they also store metadata, which contains information about the data. It contains what operations were done, what commits were done, what was the commit time and the transaction level, and schema information or the partition information, and how are you distributing a key, and where does data for a specific partition exist in your S3 buckets or like a Google Cloud Storage. So why should you choose open table formats and not just go with like plain Parquet or CSV files? So the first thing is the ACID transaction. So you storing data on blob storages, just putting them as a plain Parquet, you don't get any ACID transaction guarantees. While you're writing data to S3 buckets, if something happens and your job fails, you just have to rewrite, and you'll have to create an own process or manually go and delete half written data or like some corrupted Parquet file or a CSV file. So with open table formats like Hudi or Iceberg or Delta, we primarily use Apache Hudi in production. We have been using it for about 2-3 years now, and we have no issues. And yeah, we love Hudi for that sake. So like Hudi or any other open table formats provides ACID transactions and the CRUD operations. Like if you're storing your data in a plain Parquet, if you want to go and update like a single row or delete a single row, there's no easy way to do it. You have to read the entire Parquet file and then update or delete that specific row and rewrite the entire file. But with open table formats, they intelligently let you make that update or delete into a separate file, and then there's additional table services, mainly on Apache Hudi. They give you table services like compaction and cleaning. So what happens is you write your updates or deletes or even creates into a new file, and then an async service will pick up these files, and then they merge into the existing files, everything happening in the background. So data versioning, I mean, if you're using Parquet files, if you have to do data versioning, you just have to rewrite the entire file and then keep a map of which file corresponds to which version and everything. But with open table format, there is with the transactions, there is a way to do a commit every time you write a data to a data lake, and this commit will include information on what changes were made as part of this commit, and then where do the data actually sit in which files, and how do I reference those files and everything. So with this data versioning, this opens up for time traveling. So every commit represents a specific point in time in the timeline, and anybody querying the data can query the table as of that specific timestamp. And Hudi or other formats look into the metadata and then try and find the files corresponding to that specific timestamp or that specific commit, and then returns the data. So time travel is huge for us. Like in our case, if you want to do recommendations for workouts after your morning workout, if you want to recommend something for the evening, doing a commit specific to that timestamp helps us to do a time traveling with the data. Partition management. If you're using plain Parquet or CSV, the clients need to handle the partition. They have to manage how to store the data. Are they partitioning by time, or are they partitioning by specific key? Everything needs to be written in the client code. But with uh, these table formats, you can just write the partition key or a distribution key, and then the metadata keeps track of how to partition this data, which files contain which specific key partitions and everything. With this management definitely helps with the query planning and optimization. So when you are trying to query a specific key or a specific where condition, it can easily skip over like a bunch of files instead of going through every single file and then getting the data out of it. So there your read queries are super quicker, and then your scanning for files reduces a lot, because if you're trying to query on like Athena charges by the files scanned or the number of files that you're actually touching to get your data out of the files. Schema enforcement and evolution. Again, if you're using plain Parquet or CSV, it doesn't recognize what data you're appending to an existing file. With the open table formats, if you're trying to write a string to an end column, it just rejects and it says schema doesn't match, and you have to change the schema, or there is a way to merge schema whenever a new kind of data is coming in and you actually want to change your schema. You can do a merge schema and then your schema evolves based on your needs. Concurrency control. I said there are async services that are used for cleaning or compacting your data, like compacting your small files or removing your older versions. So these run in async, or you can even run inline while you're writing the data. But if you're running async, there might be a case where you are touching a specific file by two writers at the exact same point in time. So that leads to all kinds of problems, like you're trying to, like during a read query, there might a cleaning might be running and then your read query just exits or aborts or gives wrong data. So what happens is Hoodie or any of these table formats internally handle the concurrency, and then they know which one to prioritize first, and so that they don't return stale data or they don't try to access a file that doesn't exist. Hoodie supports this via optimistic concurrency control. It understands which query to prioritize first so that they give the right data. So do you still want to use plain old Parquet or CSV files? I think you should rethink your answer for that if you're saying yes, I want to use plain files. So the solution, the new architecture, we started using Apache Hoodie and CDC. So CDC is change data capture. So here, if you see our devices still talk to microservices and then they talk to our RDS instances or DynamoDB tables, we still take snapshots and push them into S3 buckets, mainly for backups or like rollbacks or recovery or anything. But we started using CDC on these DynamoDB tables and RDS instances. So every change that's made on these tables get captured and then they get pushed into MSK. MSK is the Kafka on Amazon. We use MSK for our Kafka needs. Once the data is in MSK, we have Spark jobs running both in streaming fashion and also like in intervals of 10 to 15 minutes. These pick the data from, these basically pick the changes from the Kafka topics and then push it, basically transform and put it into S3 and Hoodie table formats. Once they're in Hoodie table formats, we register with Glue catalog and then they're open for querying on Athena. So the tables are gated by lake formation permission. So not everybody has access to all the tables, but it's gated by lake formation permission. Once the data is on S3 and Hoodie format, you can actually register with any catalog that supports Hive, Metastore, and then you can query with Presto engines. So Hoodie or these table formats are queryable anywhere Parquet is supported. So I think most of the query engines do support Hoodie or Iceberg or Delta Lake these days. So these Spark jobs also push some information to Data Hub. Data Hub is our discovery engine. We push information on what's the schema or what was the latest update that's been made, how did the schema evolve, and how many rows does this exist. We use this for discovery and lineage to understand where is this table coming from, like which topic does it correspond to, and which source table in RDS does it correspond to, and everything. And again, once the data is in Hoodie in S3, we have more Spark jobs that read the incremental data, like what data has been written in the last 10 minutes, and then we push it to Redshift so that our Looker dashboards or our operational dashboards have like near real time information coming from a change that just happened on RDS or DynamoDB tables. Similarly, recommendation systems now have access to near real-time data or changes, and then they can run their pipelines anywhere at any point in time during the day, and then push them to devices as needed. So the impact, definitely a shorter time for dashboards. They are much more recent and much more latest. Near real-time recommendation systems, they can query data with near to no latency. Like I said, we have both batch and streaming pipelines. So based on the need, they can consume the data as they want. Again, near real-time access to data via query engines. We use Athena primarily, but you can use any Presto-based query engine. Um, and open table format enables like efficient storage and querying. So partition management for faster querying, and then storage, you don't have to rewrite for every single update or delete. You just write the updates and deletes to a new file, and then async services or async compaction services takes care of combining the files. So there's no rewrites for every single change, but then they are batched together, and then the rewrite is much minimized. The costs and the load on the primary database are reduced, so no analytical workloads ever have to hit the primary database anytime. Everything just talks to the data in the blob store. And the next one is the time travel queries for training ML models and analytics. Like I said, ML models can now train on data during middays, and basically in our case we can recommend workout based on what workout you did in the morning. We can give a recommendation for it. Like, let's say you did a yoga in the morning, we can say, hey, do you want to try doing a strength workout in the evening, and so on. So this helped us reduce latency and then faster data access for both operational dashboards and recommendation systems. um, Thanks everybody for tuning into my talk today. You can reach me out on LinkedIn or X, and here are my socials.
Awesome, Amaresh, thank you so much. We do have at least a couple of questions.
Sure.
And we're going to be passing them to you in rapid pattern. First, how do you push metadata to Data Hub?
So Data Hub, we host Data Hub on our Kubernetes clusters. We have APIs open on them, so we push metadata. Metadata includes where does the data exist, what topics does it read to, what source table it is, what kind of uh, fields or privacy fields it has, and that needs to be abstracted out or scrubbed out and everything.
We got another one here from Asus. What about costs? So first you showed us your initial architecture, and then after 20 minutes, we looked at the next one. So this next one obviously looks much more robust, rigorous, but potentially expensive. Is there something you can say about the cost increment?
So our major costs in this case are the storage on S3 and the EMR costs. Everything else is open source, like Hoodie is open source, and running like Spark is open source. So it's mainly the compute cost and the storage cost. Storage cost is something that you cannot avoid. But in our case, EMR, we decided to go with the compute cost because we wanted faster data access. It's again the trade-off. Do you want cheaper versus stale data, or a little bit costing money and then a faster data access?
We got a couple other ones. For ML models, is there a feature store separated from this architecture?
Yes, so ML teams have a feature store separated, so they do consume the data and then they build feature stores on top of that for their A/B testing and everything.
Just curious, is that something that you guys like custom built, or are you using some?
No, so like they use Feast. Feast is another open source feature store. They use Feast and then they self-host it in our systems.
Mohammed here is someone has to learn what. Okay. Where might you recommend somebody to pick up some of these skills? So, like, yeah, because a lot of people, they might not have the kind of like scale to start using like house in particular. So they might not be reading off of the read replica. So if you're not yet at that scale, you want to pick up the skills, ideas for how to do it.
Yeah, so you don't need a read replica itself. You can just spin up a Postgres server on your Docker container, just get CSV or anything with like 100,000 rows and then do an insert. You can, of course, find like dummy data anywhere online. I think even MLOps community has a course around data engineering. So you can just push it into your local Postgres and then do a snapshot. You can just start off with AWS ClickOps. Like on AWS, you don't even have to worry about CLI or anything. Just get the snapshot into a Parquet file or even a CSV file. Just click upload and push it to S3. That's it. You have your data in S3 now. And once in S3, you can try and build out a simple Hoodie table that just points to this single file on S3. With Hoodie, you can just read the data and write the data into S3 as Hoodie table format, and that's it. It's open to querying on Athena.
Thank you very much for coming and sharing with us.
Sure.
Next up, we're going to take I would say maybe 1 minute break to hear from John. Let's see if you guys see.
Yeah, you see this data lake all around here? This used to be a data swamp. It was disgusting. Thankfully, they've been doing a lot of work on the data governance side to clean things up. There used to be crocs in here, almost 10 feet long. Oh, wait. Look at this. We've got a leftover artifact. Years in the past. I don't think that guy's gonna make it much longer, sadly. This water's practically clean enough to snorkel in it. Little fella, you alright? It's definitely a croc, alright?